Okay, so welcome everyone to lecture 23. In the last class, we worked on the Eulerian form of angular momentum balance, and today I'll just give you a sketch of how to derive the Lagrangian form of angular momentum balance. I won't do the complete proof because it is similar. Okay. So Lagrangian form. The Eulerian form, you recall that it gave us that sigma should be equal to sigma transpose, symmetry. And you see, we did it with a general shape of the body, dt. dt need not be cuboid, the one that we did in the undergraduate class. It was a general body, okay, having general volume, dt. Furthermore, there was no approximation of neglecting some higher order or lower order term. Anyway, so let's see how we do this in Lagrangian form. So again, we have our body, or the part of the body, which we have been saying dt, and then the various external loads acting on it. And we have the origin of a coordinate system, let us say O, and we are doing angular momentum balance about the point O. Okay, it also has those body forces. So the first statement is obviously the same as in the Eulerian form, which is a surface integral for the moment due to traction. So that's del dt and y cross, where y is the location of a point from the origin, right? The position vector. Y cross traction, which we wrote as sigma times n day, okay, plus the moment due to body force, which is y cross b and dvy, and this is equal to dy dt of total angular momentum of the body, or the part of the body, that is dt. And again, and remember that we always apply it to a fixed set of particles. Therefore, dt is changing with time. Okay, so that's your angular momentum within the integral. Now, since we have to do it in Lagrangian form, we have to convert everything in the Lagrangian domain. Okay, so the first integral, for example, we can recall that sigma times n day is same as p times nx dax, right? And this also converts the integral from del dt to del d ref. So you have y hat cross product p nx dax, right? And then the second integral is quite simple, which is y cross jb dvx, okay? And then on the right hand side, so there's some step involved. We first convert it into dref, and ddt remains outside. And then inside we have y hat cross rho naught v hat dvx. Okay, and this you can further write it as integral over d ref, and d dt comes inside, and just like yesterday, you will have v cross rho naught v, which will cancel because cross product of two vectors, two same vectors are same, sorry, 0, so it cancels. And then the other one remains, and it is y cross rho naught times acceleration dvx. Okay, so these two integrals are perfectly fine. It's in the referential domain. We have to now work with the first one. So let us see how we can work this out. Now notice that it is very much like what it was yesterday, except that we have p and x, and yesterday we had sigma and y, isn't it? So you can recall that we tried to go back to indicial notation. So I'll very quickly do that. So we have y hat, okay, so it's a cross product. So first of all, we are going to have epsilon ijk, then y hat j, and then k component of p times nx, which is p k, let us say l into nx l, right, ei. So that's the indicial form of y cross p nx multiplied with dax. Okay, and then you have to apply Gauss divergence, and you can recall this would simply become integration over the volume, undefined volume, obviously, d ref, and you have then the divergence, isn't it? You have to first identify what is a vector which is dotted with n, and then you apply the divergence. Maybe let me do it in steps because I guess I'm rushing it a bit. So if I say that this part, if I think of it as AIL, sorry, AIL, yes, AIL, and then you have multiplied with NX comma L EI. So this is like so this whole thing is A times NX, isn't it? Where A is such that AIL is given by what I just wrote above. So when you apply cost divergence here, it is then going to become, and you see that it's in the referential domain. So you'll have a Lagrangian divergence now. Instead of Eulerian divergence, you are now going to have Lagrangian divergence. Right? And this again in indicial notation, this is del A I L over del X L E I. Right? And AIL, you already have the expression. So let's try to work out what is del AIL over del XL. So you have del over del XL epsilon ijk y hat jth component times pkl. Okay, that is AIL. Okay, so then we apply product rule, obviously, and epsilon ijk is like a constant. So epsilon ijk, and you have del yj hat over del xl times pkl, and okay, so I can put this inside the bracket, plus yj hat del pkl over del xl. Okay, I think you all agree with this. So, okay, and of course you see that this is also multiplied with ei over here. Anyway, coming back, this is then epsilon ijk, and what is this thing over here? Del yj hat by del xl. What is that? Yeah, the component of deformation gradient, right? So that's simply fjl times pkl. Okay, and what else do I say? This is then plus yj hat and del pkl over del xl. Okay, now look at the two parts separately. So this is same as epsilon ijk fjl pkl, or I could also think of it as pkl. So they are scalars, so pkl into fjl, right? Scalar a into b same as b into l, but fjl is also same as f transpose lj, right? So that's the first term, and why I have done it, because l is then appearing as inner indices, and so it's like matrix multiplication. So that was whole motive for this. Then the second one is epsilon ijk yj hat del pkl over del xl. Okay, and then of course this whole thing is also multiplied with ei, remember, because as you see here this ei, so you have that everywhere. So you can now guess what is the second term over here. Just like yesterday, this is y hat cross product divergence of first Piola-Kirchhoff stress tensor, right? Yesterday you had y cross Eulerian divergence of sigma, but now you have y cross Lagrangian divergence of first Piola-Kirchhoff stress tensor. Quite similar, isn't it? But what is this one over here? Now you see that this thing is, if you think of PF transpose, then it's the KJ component of PF transpose, isn't it? It's a KJ component of PF transpose. So yesterday we had here sigma KJ, and here we have P KL into F transpose LJ. Okay, so you can think that once you put all of them back in this equation, then you would be able to use the Lagrangian form of linear momentum balance, and things will cancel out and only one of the terms will remain, which is this thing over here. So everything will cancel out and just one of them will remain, and I'll just write that. That's integral over d ref epsilon ijk, and you have PF transpose the kg component multiplied with EI. Okay, and that's equal to 0. This has to be equal to 0. And I told you yesterday, when you do that exercise, this is same as integral over d ref, and you say axial vector and half also there, half of axial of PF transpose minus transpose is the same thing, which is FP transpose. So basically, skew-symmetric part of this PF transpose. Okay, the skew-symmetric tensor of PF transpose and take the axial vector of it. And this we are saying it is equal to 0. So this can be satisfied only when the skew-symmetric part of PF transpose is also 0. So what this has given us is that PF transpose is same as transpose of it. Okay, so that this is what you're getting from the referential form of angular momentum balance, and this is also kind of intuitive because you have already the relationship between sigma and p, right? So sigma and p, how are they related? Sigma is equal to, I guess, 1 over j pf transpose. Is that correct, or am I making some mistake? P is can someone confirm to me the relationship between sigma and p? So derived earlier. And see, the Eulerian form said sigma is equal to sigma transpose. So if you look at this relationship, it should indeed give us PF transpose is equal to transpose of PF transpose. Right? So that's why I said it's intuitive. And notice that the result of this is that P is not symmetric in general. So although sigma was symmetric, but P is not symmetric in general. Okay? So that's about the referential form of angular momentum balance. Any questions so far? So let me write down all the equations that we have gathered till now. So you have Eulerian form, and then you also have Lagrangian form. In Eulerian form, the first one was mass continuity, which tells me that del rho del t plus rho times divergence of velocity, that's equal to 0. Isn't it? And then this is the mass continuity, obviously. And then you have LMB, which is Eulerian divergence of sigma. Okay, so this plus the body force, this is equal to rho times acceleration. And you remember that acceleration is quite nasty in Eulerian form. So that's rho times del V del T plus Eulerian gradient of velocity times velocity. Okay, and finally the AMB, that is very simple. That sigma is equal to sigma transpose. You come to the Lagrangian. Mass continuity is very simple, and it is that rho hat, I'm just writing rho hat, but understand that rho hat is same as rho bar or rho that we have here. So rho hat is equal to rho naught times J. So rho naught is an extra thing here, referential mass density, which is actually known. Then the LMB is divergence with respect to x dot first pk plus j times the body force b, and that's equal to rho naught times acceleration. And acceleration has a very simple form here, which is simply del 2 y hat by del t2. Okay, and finally AMB, which tells me that PF transpose is equal to FP transpose. Okay, now let us try to see how many unknowns are there and how many equations do we have. So if you look at the Eulerian form, the unknowns, let us think of what are the unknowns. Rho is one of the unknowns, right? What else is the unknown? Acceleration is unknown, but acceleration can be thought of in terms of velocity, and velocity can again be thought of in terms of the position vector, right? So here you can say either the velocity, because in fluid mechanics, purely fluid bodies, velocity is actually the primary unknown. But sometimes if the body has solid-like nature also, for the viscous fluid, then the position vector also comes in. So I'll say v or y. Okay. What else is the unknown here? Can someone tell me what is the remaining unknown here? Yes. Sigma, right? Sigma is also an unknown. So as of now, these are all the unknowns that we have. Body force will usually be known to you. It's an externally applied load. So how many unknowns in total? This is 1, this is 3, and this is 9. So total 13 unknowns. And how many equations? 1, 3, 3 plus 1, 4. And how many does it have? This is also 3. So sigma equal to sigma transpose. So all that you have to say that the off diagonals are all equal. So it gives you 3 equations. This is 1, this is 3, and this is also 3. So 13 unknowns, but only 7 equations. Okay, so we are still short of equations, right? We still need 6 more equations if we really want to solve this. Whereas look at the Lagrangian form. You have this equation for the current density rho. And then if you look at LMB, rho naught is not an unknown, like I told you. It will be, if you choose a reference configuration, then rho naught also gets chosen. So looking at here, the unknowns are your y. See y, the kinematics y, once you know y, you will know v, you will know deformation gradient, you can know j, you can know everything. All the kinematic variables you can know once you know y. So y is the primary unknown. And of course, p is also an unknown, right? And once you know y, you see that rho is kind of, it's not coupled with the other two equations. So you can think that this is like decoupled. So in Lagrangian form, mass continuity is decoupled from the other two equations, in the sense that if you know y, you will be able to say what is rho. Okay. So that means it's a decoupled equation. So if I just talk of this one, then the unknowns are 9 plus 3, 12, right? And I'll just say in the bracket plus 1 for rho. So these are unknowns, but equations 3 plus 3, right? And in the bracket, I'll write plus 1 for mass continuity, but again, I said it's not required here. So you have 6. So again, 12 unknowns, but 6 equations. So you still need 6 more, right? So this is not done. We need to have some more relationship. Then only we can solve this. And notice that the advantage of Lagrangian form is that you don't have to solve the mass continuity equation because it is decoupled, right? The LMB has rho naught and AMB does not have rho. So that's the advantage of Lagrangian form. Whereas in Eulerian form, all three are to be solved simultaneously. But still, of course, you see that the number of unknowns are not matching with number of equations. So can anyone tell me what more equations will we be needing? Stress as a y, stress as a function of y, yes. So we have to somehow here, for example, relate sigma to kinematic variable, relate sigma to kinematic variable, or over here, relate p to kinematic variable. Okay, and this relation of relating stress to kinematic variable, this is called, constitutive equation. Constitutive. The equation that relates them is called the constitutive equation. And this constitutive equation will close the system. Okay. It turns out, a very good physics constitutive equations have to satisfy, we'll see that in the next several lectures. So we are going to devote a lot of time on constitutive equation. And what you will see is that constitutive equation has to satisfy some physical principle, which automatically ensures that the angular momentum balance gets satisfied. So I'll write here a good constitutive equation, good meaning which satisfies the physical principle. Which satisfies physical law. Okay, and to be more precise, this is related to objectivity. We'll also learn later on. Automatically takes care of angular momentum balance. So once you supply a good constitutive relation, you don't really need to solve for angular momentum balance. So when you code it in computer, in Lagrangian form, all that you need to code is the linear momentum balance. So this implies on computer, all that you need to code is LMB in Lagrangian form and likewise in Eulerian form it is LMB plus mass continuity. Okay, in Eulerian form. So you might think, what is that magic that automatically takes care of angular momentum balance? So we'll see that later on. Okay, and this is not done when you're solving it on computer. This is a differential equation, so it also requires boundary condition. Okay, you do need boundary condition also. So since it's a differential equation, we also need boundary condition.